All right, so this lesson is going to be really short. We're going to mostly talk about how to do average atomic mass, but before we do that, we talked a little bit about that in the last lesson, but Rutherford, of course, he was the one that discovered the nucleus, and he did that with the gold foil experiment. But in this case, there's the Rutherford Bohr model. Okay, so he discovered the nucleus. Remember, that was the gold foil experiment. And then a guy by the name of Niels Bohr described, oh, that's not an R. Now it's an R. Niels Bohr described electrons and the energy levels, okay? He was the first person to say that electrons exist in a specific energy level, that they can't just willy-nilly, you know, like go anywhere they want to, okay? So he is the first one to do that. When we get to Chapter 4, we'll talk about electrons and where they exist and their energy levels a lot more extensively. This is just kind of an introduction to it. Okay, but when he said that it has energy levels, he said that there's specific energy levels that they exist in, okay? And the first energy level can contain 2 electrons. The next energy level can contain 8, okay? You can actually know how many by this 2n squared, where n is your energy level, which also happens to be associated, not exactly, with your period number. So in period 1, n is equal to energy level 1, 2 electrons can exist. Okay, in period 2, energy level 2, 2n squared would be 8. And that's how many electrons can exist. Okay, so the outer energy level, which is going to be where your valence electrons are. And we'll talk about that a lot more when we get to bonding, because your valence electrons are where the reactions are or what's actually participating in the reactions. It's all about the valence electrons, okay? And the valence electrons are always going to be your outer ring, okay? So we're going to draw a couple of, it says left side, but if you just find some little space on your paper, we're going to draw a couple of these Bohr models so you can kind of see what we're talking about. So we're going to draw neon 21 and neon 22 first. So if I'm looking at neon, okay, I've got my nucleus. How many protons are in my nucleus? 10. So I'm going to say 10 protons. Let me write that bigger so you can see it better. I didn't write it very big. So 10 protons. And how many neutrons would be in there? 11 neutrons. Okay? So then I'm going to put my energy levels around there. Okay? So I'm going to start out with my first energy level. And how many electrons are contained in my first energy level? 2. So I'm going to draw an electron here and an electron here. You can draw them as dots. I just like to do them as E's so you know what it is. Okay? I draw them opposite of each other because they're both negative. And if you have 2 negative ends of a magnet, what happens? They repel. So we're going to draw our electrons as far apart as possible from each other. Okay? So that's our first energy level. Okay? So that took care of 2 of our electrons. How many more electrons do we need to put in there? 8. So we're going to draw our next energy level. Okay? So now I'm going to draw 8 electrons around there. No, I have 8 in this level. Because it's level 2, right? Okay? So now I have 8 electrons there for a total of 10. Okay? The outer part is those would be my valence. Okay? The ones inside are called core electrons. Okay? So you can draw a Bohr model for any of the elements. However, when Bohr came up with this model, there was a big problem with it. And if this is not written in your notes, you need to write it in your notes. The big problem with the Bohr model is it really only worked for hydrogen. Okay? Explained it perfectly for hydrogen. But we still use it, but it truly only works for hydrogen. So that was one of the things that sent them back to the drawing board. Like, what's the real atomic? Because ultimately we're going to get to what the final model is. Okay? That'll show up more in Chapter 4. So if I was to draw the same thing for neon 22, how would it look?
With one more on the outside.
In the outside?
Another ring.
Would it need another ring for neon 22?
Another neutron.
It would just be an extra neutron. Would look the same on the outer part, but right here,
That's not the electron.
that's a neutron. So if I was to do that right here, I would have 12 neutrons in my center and still 10 protons. And then I would still have those same outer rings. So that would be the only difference for neon 22. Okay? I believe the next one on your paper is the nitrogen, right? Is it 15 or 14? 15. So how would I draw this Bohr model? Start with the nucleus. Thank you. And how many protons are in that nucleus? So it'd be 7 protons. How many neutrons? 8 neutrons. All right. Now how many total electrons do I need? 10. Why 10? Because it's a -3 charge. So if it's a -3, that means it gained 3 electrons. Because remember, we're gaining things that are negative. So I'm going to put 10 electrons in my energy level. So I'm going to start here and do my 2, because only 2 fit in the first one. And then I'm going to draw my second one, and I still need to put 8. What do you notice about the energy levels for a nitrogen ion and neon? They're the same. That's why they take in extra electrons, because they're trying to get to a more stable form. So that's why they form ions. And we'll get way further into that as we go along, but I want you to, there's even a name for it, but I'm not going to give it to you right now. It'll just make it more confusing. But there's a name for it when you have the same electronic structure as something else, and we'll talk about that as we go further on. So that's what Bohr models look like. I hope I didn't bore you. Okay. So that brings me to atomic and molar mass. Okay. So when you look at the mass on the periodic table, we've talked about the atomic number. That's the number of protons. And remember, we always identify elements by their atomic number because that doesn't change. The protons don't change. But like you saw in that last example, the amount of electrons can. Okay. So we always identify them by their atomic numbers. Okay. But their masses, if you look, there's a decimal. Okay, the masses that are on the table are an average atomic mass of all of their isotopes, of their naturally occurring isotopes. And their percentage of abundance, or their percent abundance, is taken into account. Okay, so we're actually going to do something called a weighted average to figure out, which is exactly how your grades are calculated. It's a weighted average. Okay, but you do have to know what it's defined on, or based on. And that's this right here. Okay. So we saw that the mass of an electron and the mass of a proton are very, very, very small. And they had like times 10 to the negative 24 exponent, and then electron times 10 to the negative 28. Those are hard numbers to deal with. So they have a standard that they said they're going to use so that we can make this more, easily understandable. So 1 AMU, which stands for atomic mass unit, is exactly 1/12 the mass of a carbon-12 atoms. And carbon-12 has a mass of 12 AMU. Okay, so that way we can all relate it to. So everything's related to that carbon. Okay, all right. So with this system of relating it to that, one proton and neutron has a mass of about 1 AMU, and the electron's mass is negligible. Because remember, we said a proton was 1,800 times heavier. Okay, so they do this so that we can, and it works out great because if I go and find out the mass of something, I can figure out how many atoms and all that, which we're going to get to later. So that's how an AMU is defined. Okay, the atomic mass is the mass of one atom. Now, can we go get the mass of one atom? No, we can't. Nope, can't. I mean, you can't see one atom. Okay, you can't see one atom. Okay, so we have to do this, in a different way. So, some terms that you need to know is atomic mass has several different definitions, and it kind of depends on what you're talking about. Okay, if I'm talking about molecular mass, I'm talking about the mass of one molecule. If I'm talking about ionic mass, I'm talking about for one ion, and then if I'm talking about formula, it's for a formula unit, which might not mean much to you, but it will when we start talking about these things. We almost always, or at least me, I almost always call it molar mass, which is like the term that I can use for all of them. Molar mass, going to be the mass of a mole. Okay, and we'll decide. We'll define Monday, what a mole is. Okay, I have a song and everything. Okay, so atomic mass, okay, is always going to be rounded to 2 decimal places. Always reported in 2 decimal places. Okay. Now, for the first time ever that I've taught this class, we found this at the end of the year and we're using it. If you look at your periodic table, they're already rounded to 2 decimal places. That was to make my life easier, not yours. Because you know how many times I have to answer how to round things. On the big chart on the wall, it is not rounded, okay? And so constantly I was having to say how it rounds to things. And so we found this. It's rounded to 2 decimal places. So just use the mass that you get on your periodic table. If you lose your periodic table, they live right there underneath the paper, the notebook paper. You don't have to ask, just get one. Okay? You don't have to ask. So here is the formula for finding atomic mass. Okay? And it goes like this. You take the mass of the isotope, you multiply that by the percentage of that isotope. Okay? Plus the mass of your other isotope times its percentage. That's a percent sign. What? I don't know what you're saying. And what does the ... mean? If you have more isotopes, you keep going. Then divide it by 100. Now, if you like to take things out of the percentage before you multiply by them, you can do that, but then don't divide by 100 again. Okay? Then don't divide by 100 again. So I'm going to do an example off the worksheet. Okay? We're going to do number 2. Okay? All right, so number 2 on your worksheet says 3 isotopes of magnesium occur in nature, and it has their abundances listed. Okay, so we're going to take those isotopes and we're going to multiply mass times abundance, and then we're going to divide by 100. So it's going to look like this. We're going to say 23.98504 times its percentage, which is 78.70, plus 24.98584. If you don't have a calculator, grab one real quick. 10.13 plus, I'm running out of room, so I'm going to have to come down here, 25.98259 times 11.17. Then I'm going to take that whole thing and divide by 100. So when I do that, and remember, what did I want you to report this to? 2 decimals. So when you do that, you should get 24.31 AMU, because it has a unit, no naked numbers. Okay? Any questions? Or does it seem pretty straightforward? Okay? The alternative way to do that is I could have, you don't like to do the divide by 100, I could have done it like this, right? I could have said the mass times 0.7. I could have said 23.98504 times 0.7870 plus etc., the rest of the problem. If I do it that way, do I divide by 100 at the end? No, yeah. So whichever way you want to do that is fine with me, whichever way you like. Years ago, I found that if I just did it all and then divide the whole thing by 100, kids got better answers. But if you're handier with the calculator than some kids, then you can feel free to do it the other way as well.